We are continuing our discussion on determinants. In last class, we have looked into the physical meaning of determinants. We tried to give a definition of determinants and also spent some time on discussing properties of determinants. And this session will start with the probably most awaited thing right now on determinants, what is the formula for the determinants. And the formula for the determinants is usually given as Laplace expansion or Leibnitz formula given by both of the scientists independently at certain point of time, which says for a matrix A which has size n into n, and it I said determinant is defined only for square matrices, the ij minor of the matrix is defined as given by the term mij, which is determinant of n minus 1 into n minus 1 matrix that results from deleting the ith row and jth column of the matrix. So, for example, if I have a matrix say 4 by 4 A 1 1, A 1 2, A 1 3, A 1 4, A 2 1, A 2 2, A 2 3, A 2 4, similarly A 3 1, A 3 2, A 3 3, A 3 4, and the fourth row as A 4 1, A 4 2, A 4 3, A 4 4. Now, the minor say 2 3 minor M 2 3, in order to obtain that we have to delete the third row and second column. So, whatever is left, its determinant will be called the minor, which is A 1 1, A 1 3, A 1 4, A 2 1, A 2 3, A 2 4, A 4 1, A 4 3, A 4 4. This will be called minor 2 3 minor of the matrix, and this has a size 3 into 3, whether the minor determinant of a matrix 3 into 3 or whether the original matrix was 4 into 4. And then comes a term cofactor. Cofactor is given as Cij, which is C2 3 will be minus 1 to the power row plus column id 2 plus 3, which is basically again minus 1 m 2 3. So, now when we calculated the minor and cofactor, that will be utilized for calculation of the determinants, and this is given as the formula for determinant is given as summation of all the row terms into cofactor for each of the row components. So, we have to consider one particular row and then calculate cofactor of each of the terms in that row and multiply with the elements of the row. Instead of row, we can do it any column also, and this summation will give us the value of the determinant. Now, if we think of calculation of determinant, so it needs calculation of further determinants. For example, the earlier example that we have given A 1 1, A 1 2, A 1 3, A 1 4, A 2 1, A 2 2, A 2 3, A 2 4, A 3 1, A 3 2, A 3 3, A 3 4, A 4 1, A 4 2, A 4 3, A 4 4. In order to calculate its determinant, first I have to delete, say for example, first row and first column, and I get a minor matrix, and then I have to calculate the determinant of this minor matrix and multiply with ij minus 1 to the power I plus j and multiply with this particular row which is 1 1 element, and then I will take each other term of the row and calculate their minors and cofactors subsequently. So, one determinant needs calculation of several other determinants, and determinant of the sub-matrices. For this 4 by 4 matrix, it needs calculate of this 3 by 3, maybe then we will delete, for example, later we will delete this row, this column and this particular row, and then calculate matrix which will have this column, this column, this column and its determinant. So, calculation of several determinants. Therefore, if we start with a large matrix in mind like 100 by 100, we have to calculate cofactors of 100 terms of each row, one particular row or column. So, that means we have to calculate 199 into 99 matrix determinants. Again, each 99 into 99 matrix will need calculation of 99, 98 into 99 size matrix determinants. Therefore, there will be a loop of calculation of determinants, and finally, we will reach to a smaller matrix like which will have 2 into 2 or 1 into 1 size. For example, if I think of calculating determinant of this particular matrix, I will first delete this column, this row, and I will get a smaller matrix like this, which is now 2 into 2, and therefore, its determinant can be calculated easily A33 A44 minus A34 A43. And then these determinants will be plugged back, determinant of this multiplied by minus 1 to the power 1 plus 1, which is 1, into this will give me one component of the determinant of this 3 by 3 matrix. Then I will take this row element and the cofactor, this row element and the cofactor, and finally get this 3 by 3 matrix. So, we will get all the 3 by 3 matrix determinants which are cofactors of 4 by 4 matrix determinant, and so on. We can finally calculate, go back to this 100 by 100 matrix we are considering. So, this calculation is not very straightforward one, especially for large matrices, and we have to use something like a computer program for large matrix, and we will see later that all large matrix calculations, even for solving large matrix equations, we need to write any form of some form of computer program. Okay. Now, we will see some of the application of these determinants, at least why this complicated calculation will be needed at certain cases, and one of that application is finding an inverse. So, if we write the formula for finding determinant, which we discussed in last slide, is that the element in one row into its cofactor, the next element in that row into the cofactor, so on. For each row, I can get a same formula like this, the elements of the row multiplied by the cofactor gives the determinant, and therefore, we can get n, if there is n by n matrix, n equations for n each rows, where the right hand side in all the cases are determinants, and this equation now can be expressed as a matrix form, where A is the original matrix, matrix A, the cofactors are ordered along like in a transpose manner, that is C11, C21 up to Cn1 comes in one row of the matrix, and C11, C12, C1n, which are ideally row cofactors of each row of A1, 1, 1, 2 comes as one column. So, this we can say transpose of the cofactor matrix, and this gives us a matrix diagonal matrix. This is a diagonal matrix, each entry is determinant of A. So, we can say that this matrix, the right hand side matrix, is nothing but determinant of A, which is a scalar, determinant of A, which is a scalar, and this multiplied with an identity matrix of size n into n. So, we can further say the following matrix equation, this matrix equation can be written, which is basically expression for determinant of A matrix using each row and its cofactors, and this will give a formula. This matrix equation is matrix A into transpose of the cofactor matrix C transpose is determinant of A into an identity matrix. A into C transpose is determinant of A into identity matrix. So, we can divide both sides by determinant A and can write A into C transpose by determinant of A is an identity matrix. A into anything which gives an identity matrix is the inverse of A, and therefore, we can write A inverse is a transpose of the cofactor matrix divided by determinant of A. So, this is one way we can utilize the matrix, the determinant, to find out matrix of an equation. And now, once we can find out the determinant and cofactors, of course cofactors are needed to find the determinant, we can find the inverse of the matrix. And once matrix inverse is found out, now we can have our probably first proposed matrix solver, that Ax is equal to B system equation system is given for Ax. A is a large matrix, X column has large number of vectors, so that we cannot solve them directly. X is equal to A inverse B, where A inverse is calculated through determinant and cofactors, and X is now the solution. So, this is one matrix solver technique where find out A inverse and multiply with B to get the solution X. However, calculation of determinant and cofactors we have seen for large matrices involve large number of computation, because each cofactor comes from a submatrix whose determinant again cannot be directly calculated if it is not 2 into 2 type of matrix. Again we have to get cofactor of the sub matrices and calculate its determinant and go up to a 2 by 2 or 3 by 3 smaller matrix. So, it involves large number of computational steps, and sometimes these calculations, multiplication of so many numbers, finding out a number of determinants and adding them up after multiplying with the row elements, this needs very large number of computation, and sometimes it may be limited by the practicability or the resource. For a simple desktop computer, I might not be able to solve a 1000 by 1000 system by finding inverse in for example, in a couple of hours. It might need very long time for the calculation. So, these are not very elegant way of solving matrix equations and mostly restricted due to the resource limitation and also practicability of the solution, and that is why we need to investigate other matrix solvers. So, again determinants can be applied to find out matrix solution of matrix equation in another method also, and which we I am going to discuss, that will gives us a very famous rule of solving matrix equation called Cramer's rule. So, if I have a equation Ax is equal to B, we have discussed this can be expressed as summation of column vectors multiplied with coefficients x1, x2, xi, xj, xn. So, a linear combination of column vectors gives us the solution vector, the right hand side vector B. So, B is a linear combination of columns of A. Now, what will happen if I take away one column of A and replace it by B, or I have the matrix equation Ax is equal to B, I take jth column and I take this jth column and substitute it by B, what happens to it? And we can see column B, we know that column B is a linear combination of columns of A, that is why how the matrix equation is there. So, B has components along all the column vectors of A. So, there are combination B can be expressed as combination of column 1 like column 1 into a constant plus column B into a scalar plus column 3 into a scalar up to column n into a scalar. So, we can write it as a combination of column 1 to j minus 1, column j plus 1 to n, and also column j, a combination of all columns basically. So, we can decompose B in two parts, one is A, another is B, where A is combination of all columns except j and B is contribution of column j. And what is the contribution of column j? If we go back to a previous slide, we can see contribution of column j vector is nothing but xj, xj amount of column j is multiplied to get B, one part of B. So, contribution of column j is xj. So, now we can say this is linear combination of columns except j, and there are different x1, x2, xn, different amounts are scalars are multiplied with other column vectors, and xj is multiplied with column j. So, if we replace column j into A by B, the resultant matrix now can be decomposed as, or can be written as, that A is the jth column is now replaced by B1, B matrix. So, B matrix has one part BA and BB, and now if we see, wait a second, if we write A, A has one part which is B A and another part which is x j into A1j, x j into A2j, x j is basically the scalar multiplied with the column j. And therefore, if I try to take it is A has two part, one is like the jth column of A has two part, one is combination of all other column, another is combination of the component of B along column j. This is not column I, this should be column j, this should be column j. So, if I try to take its determinant, and we have discussed about different properties of determinant, that the determinant can be expressed as if we decompose column into a row into two part, the determinant also can be decomposed accordingly. Therefore, the determinant will be one part of the determinant is due to the combinations of all other columns except j, another part is due to j. And so, this is property 3 which we discussed in the properties of determinants. This part is a linear combination of all columns in this matrix, because B A is combination of all other columns. So, this is as this is linear combination of all other columns, the determinant must be 0, and we have seen it earlier. And the right hand side is a multiplication of x j with one particular column. So, we can take x j out of it, and this will be nothing but the original matrix A. So, the determinant of A j, which is jth column replaced by B, will be 0 plus x j into determinant of A, and we can now write determinant of A j is x j into determinant of A. Therefore, x j will come out as determinant of A j divided by determinant of A, and we can do it for column 1, column 2, column 3 up to column n, and can get different values of the like of x1, x2 up to xn. And this is given as very famous Cramer's rule. The jth component of solution x to the equation Ax is equal to b can be obtained as the ratio x j is equal to determinant A j, where A j is by determinant of A, where A j is replaced by column j in A. Where A j is obtained by replacing the column j of A by the vector B, as this is the form of A j. Now, this has been utilized for certain cases, at least for not extremely large matrix, but for some larger matrices to find out the solution, and it directly gives us the solution of x is equal to b. However, if A has determinant 0, then it will not give us any solution, and there can be cases when A is a singular matrix. Will we, of course, Cramer's rule will say that the solution is either infinity something by 0, or it might be determinant of A j is also 0. So, it comes to a 0 by 0 form. So, Cramer's rule cannot give us solution in case of determinant of A is 0, and we have to see what actually happens to the equation system when determinant of A is equal to 0, or the cases when the equations will not have a solution, or maybe we will see some of the cases where the equations have infinite solutions, and all these cases link with determinant of A is equal to 0. So, one very important utility of the concept of determinant is to identify an equation system which has no solution, or which has a unique solution, or which has infinite number of solutions. So, we will have a quick discussion on the cases when we have different type of solutions, like what will be we can call existence or uniqueness of solutions of x is equal to b, and calculation of determinant of A will play a very vital role on that. So, we quickly look into a concept called rank of a matrix, which comes from again calculation of determinants, we will see, and solvability of the equation x is equal to b. By the term solvability, we will see the case whether the equation x is equal to b is at all solvable, whether the solution gives us an unique solution which is desired in many cases, or there are cases where multiple solution exists, and in terms of multiple solution you will see infinite number of solutions exist in certain cases. So, we go to the equation systems, and we start with looking into representation of the equation system, or when a physical system or a vector algebra can be represented as a matrix equation. So, we start with the most primitive form of combination of a linear equation system, which is two straight lines crossing each other, has equation, one has equation 2x minus y is equal to 1, another has equation x plus y is equal to 5, and if we solve this equation we get the intersection point. Now, and this is the equation represented in the matrix form. Now, solution is not possible if the lines are parallel, there will not be any intersection point. If one line is coincident on other, any point on that line will be a solution. So, there will be infinite solution. So, in cases the lines are parallel, there is no solution. In case the lines are incident on each other, which is basically in both the cases lines have exactly same slope. This first case lines are parallel, no solution, lines are coincident, infinite solution, and if the lines have different slope, then definitely they will meet at certain point, they will intersect each other at certain point, and we will have a solution. So, no slope, same slope is no solution or infinite solution, and different slope gives us a unique solution. And this is a row wise representation, because each equation gives me the members of each of the rows. If we look into the column wise representation, it is basically two vectors, a linear combination of two vectors. First vector is the column 2 1, second vector is a column minus 1 1, and I multiply 2 1 by 2 times and then add minus 1 1 by 3 times, I get the point 1 5. So, 1 5 is the x is equal to 2, y is equal to 3 is the coefficients multiplied with each of the columns, which is giving me the resultant B column. And in which case there will be no solution or infinite solution, when the column vectors are in the same direction, then there cannot be any solution if B is in a different direction. For example, if this is 1 5 is the B vector and I have one column 2 1, another column vector 4 2, no way I can add this to have a linear combination and find out B. So, if the column vectors are in one particular direction and the B vector is in another direction, there is no solution. If the B vector is in the same direction of the column vectors, if column vectors are in same direction and B vector is in the same direction, there are infinite solutions. If the column vectors are at two different directions, for any B vector I can express it as combination of these two column vectors, linear combination of these two column vectors, and I can get a solution. So, again here the solutions when the column vectors are in the same direction. If B is on that direction, there is infinite solution, otherwise there is no solution. We can have the same thing represented for a 3D case. In a 3D, the row based equation system will give us equation of 3 different planes. If the planes intersect at one particular point, there is a unique solution. If they do not intersect at one particular point, there can be two cases. If the two or more planes are parallel, but they are not coplanar, so that these planes are never intersecting, we will have no solution, or there can be a third case, they are not coplanar, but line of intersection of they are not parallel, but line of intersection of one plane or two planes is skewed to the third plane, and then there will not be any solution. And if all the planes are coplanar, any point on that plane will be a solution, there will be infinite solution. Similar thing we can say that will happen for combination of vectors, that if I add 3 vectors a1, a2, a3, I will get the third vector. There is no solution when like if ABC is a linear combination of the other two, there will be no unique solution. For example, if ABC one vector is combination of others, then there will be basically two independent vectors, which is creating a plane. So, for example, we can have a case like this is vector A, this is vector B, and this is the plane containing vector AB, in which C is a member. So, C is basically alpha A plus beta B. Now, if D is orthogonal to that, if D is here, there is no combination of A, B, C which can form D, there is no solution. Or if say this is D1, if D is again on the plane, then there is an infinite possible combinations which can give us the solution. So, we can see that there are cases of no solution and infinite solution, and these cases have some similarity. The planes are parallel. If they are coplanar, then no solution. If they are coplanar, then infinite solution. If they are parallel but never meets, then they have same angle of inclination but never meets, which means they are parallel, they are infinite solution. If third vector is combination of first two vectors, then there are infinite solution if the solution vector is also a combination of first two vectors, if not there are no solution. So, now we will see that what we call solvability of the equation. Ax is equal to b has unique solution if rows or columns are linearly independent. All the planes are in different angle of inclination, all the lines are in different angle of inclination, no column can be expressed as resultant of combination of other columns. So, that is what is called that they are rows or columns are not linear combination of any row or column is not a linear combination of other rows or columns of A, and in this case the matrix is non-singular and A has a non-zero determinant. Now, if A has a zero determinant, then there will be either infinite solution or no solution. And now, we have to see how can we distinguish between the cases infinite solution or no solution. We look into x is equal to b where determinant of A is 0. That means, one row is at least one row is linear combination of other rows, or at least one column is linear combination of other columns, and A has can have infinite solution, can have no solution. No solution in case of parallel planes, infinite solution in case of coplanar planes in 3D. No solution if vector b is a linear combination of column A. If vector b is also like one of the column is linear combination of other columns of A, vector b is not a linear combination of column A, no solution. If vector b is also a linear combination of column A, then there are infinite solutions. So, we need to replace, we have to check whether vector b is a linear combination, whether vector b is a linear combination of columns of A, and these things are happening when determinant of A is 0. That means, at least one column of A or more than one columns of A are linear combinations of some other columns of A. Now, we have to see whether B is also a linear combination of A. So, one column of A is linear combination of other columns of A, that means determinant of A is 0. Now, if we replace that column by column B, if column B is linear combination of all other columns of A, the determinant will be still 0. If it not so, then B is not linear combination of other columns. So, we need to replace a column of A with columns of B and check the determinant, and 0 B will say that it is linearly dependent. Now, it might happen, say I have 4 columns of A, A11, A12, A21, so on, A12, A22, so on, A31, A32, so on, and A41, A42, and so on, and this is my B1, B2, so on. Now, maybe this is equal to alpha C1 plus beta C2. So, I take this is a determinant of A is equal to 0. Now, if I replace first column, if I replace the first column by the column vector, by the B vector, the determinant will be still 0. So, I will see that the determinant is still 0, I cannot make a decision. If I replace third one, the determinant will be still 0. Only if I replace the second column by B, the determinant is non-zero, because B is not a linear combination of 1, 3 and 4. So, I have to check with each column, I have to replace each column by determinant of B and see whether the determinant is non-zero. If I see all the determinants are non-zero, then I will say that 0 B the 0 determinant is linearly the B is linearly dependent on B. If non-zero, then I will say that B is, else non-zero implies that B is not linearly dependent on columns, and then B cannot be expressed as a linear combination of columns of A, and therefore, there will be no solution. In the other case, when B is linearly dependent, there will be infinite solution, because unique solution case has been ruled out as the determinant of A is already 0. So, we go to the next slide. We define a term rank of a matrix, which is rank of number of independent rows or columns of a square matrix. Consider a matrix n into n size and all its minors and further minors, etc. If determinant of A is non-zero, it has rank n. In case determinant of A is 0 and any of the matrix of the minors is not 0, it has rank n minus 1. If determinant of A is 0 and first minors are 0, we have to see the minors of minors. If they are non-zero, then we will say rank is n minus 2. This is basically a way to find out what are the number of independent rows and columns. And A 0 matrix will always have rank 0, and A n into n, if it has rank n, we call it a full rank matrix, and we will say that it will have a unique solution. So, how will we calculate rank? For example, I have matrix A11, A12, A1n, A21, A22, A2n, An1, An2, Ann. I will check what is this is A, whether determinant of A, what is determinant of A. If it is non-zero, rank is, if it is 0, then I will consider the minor matrices like this. If they give a determinant non-zero, rank is n minus 1. Otherwise, I will take a smaller minor matrix, sub-minor matrix. If that gives non-zero determinant, then rank is n minus 2, so on, and we can find out what is the final number of independent rows and columns, and that will be rank. If all the elements of a matrix is 0, it will automatically have a rank 0, otherwise it will have at least rank 1, at least if there is one non-zero component. And if n into n has rank n, we call it to be a full rank matrix, which will always give a unique solution. So, if A rank of A is n into n is n, Ax is equal to B will always have a unique solution. If not so, we have to check the matrix AJB, which we have done while finding out solution of the matrix. Column J, the jth column of A is replaced by B. We have to check AJB where jth column has been represented by B, and we have to check all such matrices for different values of J. Now, if for any of J the rank of AJB is equal to rank of A, which is not equal to n, we have ruled out the case rank of A is equal to n, there is no unique solution. In that case, rank is not is equal to n, there are infinite solution, else there it has no solution. And we call, if there is no solution, then x is equal to B is called an inconsistent system of equation. This equation system is not consistent, therefore, there is no solution. So, these are very important three cases. If A is full rank matrix, there is a unique solution. If A is not a full rank matrix, but rank of A is same as rank of AJB, where any column like J is replaced by B, we say it has infinite solution. If A is not a full rank matrix, but rank of AJB is greater than rank of A, we will say there will be no solution. So, now we will start looking into cases, what happens, how will be when x is equal to B, solution of x is equal to B when there are infinite solution or when there are unique solution. Of course, no solution cases are usually been ruled out, but there are some methods where you can find out the best solution or the most optimized solution when no solution actually exists there. What is the most optimized solution, what is the nearest solution, and we call that best solution. We will start looking into different solution methods in the later classes. Thanks.